This is a flip video about the VESPR theory and building molecules. So to begin with, there's a couple names that we can also use for this video, and that is molecular structure or geometric structure. So we're going to learn how to actually make the different shapes of the molecules that really exist versus just the one-dimensional ones we draw on our paper. So VESPR stands for valence shell electron pair repulsion. And so just like the name indicates, we're actually talking about the electrons arranging themselves in a way so that they can exist together, but remember that like charges, electron and electron want to repel. So they position themselves around the atom in a way that they can exist, but still be the maximum distance apart from each other. So we've been drawing our structures very much one-dimensional like here, and so we're going to learn how to actually put them in their correct shape as seen here. This idea right here, the molecular shape, is based on this VESPR theory of the electrons positioning themselves in a way where they repel and they're at the maximum distance but can still exist together. Okay, so let's take a look at water. So here's the Lewis dot structure of water, which you know how to draw, or maybe you're drawing it with sticks already and the lone pairs around water. So this is not an accurate representation of how water actually looks in the correct shape. This is just a Lewis dot structure. Water actually has a shape, and in order to determine the shape of water, we need to look at two things. So anytime we want to know the shape of a molecule, these two things are important. How many atoms are there around the center, and how many lone pairs are there around the center? So it all involves the center, okay? So let's take a look. Here we go, our two questions. Atoms around the center. Well, here's the center, and there are two atoms around the center. Lone pairs around the center. Well, here's the center, and there are 1, 2 lone pairs. So we've got a combination of 2 and 2. So anytime you have a combination of 2 and 2, you make a specific shape. And that shape for water is called bent. Water is always bent. So if you notice, the bonds, instead of being linear across here, kind of bend down, and these extra lone pairs pop up here, kind of like bunny ears. This now is the correct position following the VESPR theory, meaning the electrons, remember each bond holds 2 electrons, electrons here, electrons here. These electrons repel from these, and these repel from here. So everybody tries to align themselves in a spot that allows them to exist together. And there's an actual angle at which this happens. And we call the angle at which this happens a bond angle. These bonds position themselves at about a 105-degree angle. When we built this in lab, this molecule is going to look like this. So if you notice here, I have a red sphere and 2 white spheres. And the red sphere had 2 bonding sites, and the white sphere had 1 bonding site. So this is a bent structure. Okay. Next, there are some more structures. The next one we're going to learn is linear. If you notice up here in the corner, I've drawn the correct Lewis dot structure of CO2. Double bond, double bond. But when we look at shapes, double bond and double bond, doesn't matter if you have double bond or a single bond. It's all about the two questions that we ask, and that is how many atoms are around the center and how many lone pairs. So let's answer these questions. How many atoms around the center? Well, here's the center. So there are 2 atoms around the center. So far 2. How many lone pairs? 0. Right? The center has no lone pairs. Remember, these are not considered center atoms. So these are non-bonding pairs, but they're not the lone pairs around the center. So therefore, when I put together my 2 and 0 combination, I get what's known as linear. If you notice here, black represents carbon. And if you see here, I have these little bendy bonds that allows me to double bond these 2 oxygens. So linear. And this is how I would draw it on my paper, linear. And if you notice, the angle at which the bonds are at is 180 degrees. Okay? All right, next, I have tetrahedral. So here we have here methane, and I've drawn the correct Lewis dot structure, CH4 seen here. How do we actually make this with a correct shape? Well, I asked myself two questions. How many atoms are on the center? So let's see here. Here's the center. The answer is 4. And how many lone pairs are around the center? Well, none. All the bonding sites are taken. So 4 and 0 make tetrahedral. If you hear the word tetra, that prefix actually stands for 4, so that can help you with this one. And if you notice here, I've got a structure that looks like this. Kind of hard to draw, so I like to show it, seen here. Here's tetrahedral. So I have a carbon, black carbon here in the center, surrounded by my white hydrogens. Okay, so I have one sticking up, 2 on the side, and then 1 in the back. And you notice I make kind of a dash line to show the 1 in the back. That represents it going backwards. And the bond angles seen everywhere. Here, here, here. So all the bond angles are about 109.5 degrees. Okay, moving on to the next one. There's 2 more. Here's the next one, trigonal pyramidal. And I'm using BF3. Now don't forget, boron is an exception. Remember, it only has 6 electrons and it is stable as opposed to 8. It doesn't have to fulfill the octet rule. So I correctly have 2, 4, 6 right there. Boron does not fulfill the octet rule, and that is okay. It is still stable. So if you notice then, I've got 3 atoms around my center. There's my center, 1, 2, 3. You don't count the center. So I've got 3. And how many lone pairs are on the center? Remember, none. Tricky, tricky. You have to be careful. Boron does not need that extra pair. So I have this shape seen here. And as you notice in my model, I've used the purple for the boron, and the green for fluorine. Green can be used for any of the halogen families. And notice there's nothing that indicates I have any lone pairs up here. Nothing. So I'm good to go with that. So these all make 120 angles. And this is how you would actually draw it. Okay, so it's a little bit easier to draw this one. And the last one seen here is trigonal pyramidal. And I've used NH3 as my compound. I've shown you how I would draw it on paper with a Lewis dot structure. And yes, in fact, I do have a lone pair. Remember, nitrogen needs 8, 2, 4, 6, 8. So now my 2 questions. 3 atoms around the center, 1, 2, 3. And 1 lone pair, 3 and 1. So as you see here, I put nitrogen in the center, and I've angled out 3 hydrogens like a pyramid style. Right? Kind of looks like a pyramid style. And then I've got my lone pair on top, and I kind of do this little lobe up here. And so my structure now, 3 and 1, is going to look like this. And if you notice here, there's something that indicates I have something extra on top. And a lot of times in some of the model kits, there'll even be this little lobe that you can attach on to indicate a lone pair up there. So this is trigonal pyramidal. Don't forget, these are the questions you have to ask yourself. As you notice, I have indicated some colors that can help you in lab when we actually make these structures. These combinations that I've just mentioned, 3 and 1, 4 and 0, these are the combinations you're going to have to remember and memorize to the actual shape's name. If you know the combinations, you can always figure it out by drawing the structure and counting. Those you will have to memorize.